Oh, cool. Okay. Perfect. Thanks. Yeah, so I work at Southwest Research Institute. We are an independent, not-for-profit research organization based in Texas in the United States. We're also a founding member of the ROS Industrial Consortium back in, I think, 2012. So a little bit of background on us. We work a lot in applied R&D across a large spectrum of disciplines in engineering, everything from deep sea to deep space, as we say. Which also includes robotics. So in terms of the types of robotic systems that we work on, we're really focused on trying to deploy robotic systems in places where traditionally it's been really difficult. So for us, this is primarily trying to work in dynamic manufacturing environments where we can't fixture parts or parts don't come out the same way every time, and that there's some element of a dynamic environment involved. And also trying to deploy robotics for places where it's also difficult to hire people with hard to find skill sets, as well as trying to deploy robotics for dangerous or dirty environments. So those are sort of our focus areas, and so we do a lot of work there. And also building custom robotic systems, whether they're large mobile robots or sort of non-standard robotic systems that leverage manipulators and other external axes and things like that. So briefly this. So, we're involved in ROS and ROS Industrial because we've had sort of all the same challenges as most of you have probably also had, right? Where there's a lack of interoperability, where we're having to rewrite software for robots all the time, where we're trying to work in environments where it's difficult for traditional robots to exist. And so that's what's really gotten us involved in ROS and ROS Industrial in the past. And so we're trying to leverage so all the cool capability, advances in perception and motion planning and all those sort of things, and trying to bring those together into robotic systems that can do things that they've never done before. So that's sort of our organization at a really high level. So over in the America side, we do a lot of work on surface processing with robotics. And so a lot of our applications fall into the sort of paradigm that we call scan and plan. So the idea there is that we want to be able to present a part to the robot that it's never seen before and have it be able to do some sort of meaningful task, usually some sort of surface processing like sanding or painting or grinding or inspection on this particular part, and have it be able to handle variances in parts, have it handle variances in the environment. And so this process for us kind of looks like this flow chart here, right? So we somehow define nominally what our environment is, what sort of robot or robot system what we're using. And then we want to actually do some sort of surface reconstruction with a vision sensor, usually. So there's some motion planning involved in scan execution. And then some sort of surface reconstruction where we try to take all this data and put together a model of the thing that we just looked at. And then from there, infer how are we going to do this process, whether it's sanding or painting, come up with that sort of logic and do the motion planning and then have it execute autonomously. And so we do a lot of work on all the various pieces that go into this process, as well as sort of the application level of this. So again, here's some sort of the stages of that process, right? So we want to use some sort of sensor here on the top left. We're sort of scanning over a part and trying to do a reconstruction of it live, right? And so then when we have that reconstruction, an operator or an application itself can go in and say, okay, well, I'm really interested in creating some sort of like surface coverage toolpath on a particular area. And so that involves a lot of like data processing, again, surface reconstruction, but then also toolpath planning to figure out, hey, where does the robot actually need to take its tool to do this process? And so from there, we have to develop a motion plan, right, where we tell the robot how do you go down and execute that toolpath. And so that's where we're using some of the motion planning capabilities in MoveIt and Tesseract to come up with collision-free and hopefully close to optimal trajectories for executing whatever the process is. And so we also take into consideration process constraints there as well. And then after the fact, we also do a lot of work with sort of the processing of or the evaluation of the process itself. So trying to develop things like vision classifiers to tell us how well that we're doing the process that we're executing, so we can actually have sort of a closed loop here and ensure that the process that we're doing is done correctly and that there's no rework that has to be done by these robotic systems. So over the years, we've developed sort of different scan and plan applications, mostly in ROS-I. And so we've taken all that same pipeline, all those tools, and updated them and turned them into sort of this ROS-II incarnation that we're calling the scan and plan workshop. And so we initially presented this as a workshop at ROS World in 2021. So that was with the hardware setup shown on the left here, a big Motoman robot and PushCorp end effector doing some sort of polishing operation on an aircraft part. And then we took that framework, we added some new capabilities and refined it a little bit, and then created this demo that we presented at Automate this year in Detroit over the summer. And so this is a video kind of our consortium lead, Matt Robinson, running the system here. So again, the idea is similar. We have a real sense on the end of this robot. We've got sort of these arbitrary different parts that are traditionally pretty hard to do a surface reconstruction of because they're really bright and they're really specular. So using sort of our updated surface reconstruction tools to come up with a model of this, and then giving the operator the ability to select on that model, hey, I want you to go do, some sort of surface finishing task, in this case polishing on that particular area, and sort of integrating all this into like a standalone application. And so we've got our GitHub link down there at the bottom as well. And so all this code is open source. And so the idea on our side is that a lot of our consortium members are really interested in these sort of scan and plan applications. And so we wanted to put this together as an example that we could use in training and other applications to sort of use it as a template repository for people trying to develop scan and plan applications. So definitely go check that out if this is something that you're interested in. We also did a developers meeting about the inner workings there. It's linked on there as well. But we've made a lot of improvements to the various parts of the scan and plan application. So I want to touch a little bit more on what those are. So the very first piece here is surface reconstruction. Like I mentioned, this can be really difficult for really like bright and shiny and specular parts. So we have done a lot of work creating sort of a new pipeline for surface reconstruction, and we put this together in a repository that we're calling Industrial Reconstruction. But it leverages some tools from Open3D, basically streams of depth images and color images are piped into the system with TF transform updates, and the result is that you get a semi sort of live surface reconstruction that's fully colorized and does a really great job on specular parts. So we've got some examples here on the bottom of a titanium machine component that we had in our labs that we've had a really, really difficult time imaging in the past, and so we kind of use this as a benchmark for our surface reconstruction algorithms. But it does really, really well for bright and specular parts, and it also does really well for sensors with a high noise level. And so we've been using the RealSense quite often in some of our recent applications, and it does a really nice job of producing smooth meshes given that sort of data. So I wanted to highlight this as a really nice improvement if you're looking for tools for doing surface reconstructions of arbitrary parts. And I also wanted to sort of bring some attention to these other tools as well. So we've been leveraging Open3D for a little while now, and it's been a really nice alternative to PCL for various types of point cloud processing tasks. We also use Cloud Compare a little bit as well, if you guys are familiar. It actually has a core library that we built into a Debian and provide on our ROS-I PPA site there. But some really good tools for point cloud processing. So some additional improvements, sort of stepping on beyond the surface reconstruction step into toolpath planning, right? We want to take this arbitrary mesh that we've created and then generate nice, generally raster patterns of waypoints on our surface. And so we made a lot of improvements to our toolpath planning library called Noter. It's also linked here. And so some of these improvements that we've made now are trying to port it to ROS-II. And so the general idea for this is that we've actually sort of extracted the ROS components from this library and then put the ROS interfaces back on top. So we've re-architected this a little bit into a more customizable toolpath planning solution. So our idea here is that we've got a pipeline for motion planning where first, we want to make some sort of modifications to our input mesh, whether that's smoothing or segmentation or region selection. So that's goes into the mesh modification. We take the output meshes there and generate toolpaths on them. And so we've got several different implementations of planners, things like raster planners and edge planners. And so those can produce toolpaths for us. And then afterwards, we've got a step where we modify those toolpaths if we want to do maybe orientation smoothing or we want to flip the direction. So basically, these are all interfaces for our toolpath planning library. It's also plugin based as well. And so we developed this GUI that's being shown on the bottom, where you can essentially load in a GUI that controls this pipeline, and you can select what plugins you want to use and configure them all there online, and then be able to quickly sort of iterate through parameters to see how those changes are affecting your toolpath and really dial down on what those are. We also did a little bit of work here on improving our region of interest selection tool, and so that's the video that's shown up top here. So a lot of our systems use some high-level operator interface to allow the operator to say, okay, hey, I want to do some sort of task in this general area. And so we've been using this tool as a way for operators in the RViz environment to go select regions of interest that they're interested in working on. And so that's sort of coupled with the toolpath planner as well by being able to extract sections of a mesh given that definition. So some cool improvements there. I'll come back to that slide here in a second. But we also do a lot of work on Tesseract, which is our motion planning environment. So for those of you who are unfamiliar, it's a motion planning environment. It's very similar to Move It, but geared a lot more towards these sort of industrial applications that we encounter with a lot of our applications. So some differentiating features of Tesseract versus Move It are, it's cross-platform, it's ROS independent. And so it makes it a little bit easier to deploy on different types of operating systems and things like that. We've also done a lot of work on the collision checking there as well, developing different plugins for collision checking to really try to optimize how that's done, the amount of time it takes to do collision checking for motion plans. And the environment is set up a little bit differently as well to be fully mutable. So you can fully change or build up an environment dynamically. So if you wanted to do, say, a tool change for a robot, it's really easy to cut off a section of your robot sort of links and move them to a different joint, or introduce something new into the environment as well. But I think probably the coolest and most interesting aspect of Tesseract is the motion planning pipeline that we've gotten set up. We tend to do a lot of what I call multimodal motion planning. It's kind of a weird term, but essentially trying to leverage different types of planners to come up with a nice hybrid plan. So that's maybe running OMPL to come up with a free space plan, but then using TrajOp to do optimization and really produce a better, more optimal trajectory in terms of smoothness and jerk and things like that. But then we also use these different pipelines with Cartesian trajectories as well. So like the demo with the puzzle piece, we're using first the Descartes motion planner to come up with a roughly optimal solution, and then using TrajOp to really smooth that and take advantage of some of the loose constraints that we have on that particular application. And so that's kind of what we're showing on the graphic on the top right, is that we have the ability to create all these really custom motion planning profiles and paths to really tailor it to the application. And so that's been a real big game changer for us in terms of being able to make really nice motions that are customized to some of the applications that we're seeing here. We've also made quite a few updates to our Descartes motion planner. So for those of you who are not familiar, this motion planner is actually really good for under-constrained Cartesian waypoints. So if you have something like a raster pattern on surface coverage, and you have a robot or an application that doesn't use the full degrees of freedom of your system, so say an application where you have freedom about the tool z-axis and you have a 6 or 7 or 8 or 10 DOF robot, you have to do kinematic redundancy resolution. And so Descartes is a tool that we use to do this, to really come up with more optimal trajectories. But recently we've been using this again, sort of that multimodal planning paradigm, where we're trying to use Descartes to come up with a really quick solution that's we know is not optimal, but try to use that as a seed trajectory for TrajOpt or an optimizing motion planner to really make that a lot better. So some updates that we've added to this, again, it's cross-platform and ROS independent. And we've sort of reintroduced, we've got our own sort of dynamic programming algorithm that searches this graph to come up with a solution, but we've also reintroduced a lot of sort of traditional search algorithms from Bruce Graph Library, trying to expand some of the capabilities that we have there. Yeah, so then branching out a little bit from the scan and plan sort of tools and application that we've been developing, we also have a variety of other projects that we're contributing to. And so I'll breeze through these quickly in the interest of time. But one of these is a reachability analysis tool. And so we've been doing quite a bit of work on that recently, sort of extracting the core pieces, making them independent of ROS, and then adding these ROS-I and ROS-II interfaces. So we've added some new evaluation metrics to this, updated the visualization, also added a Python interface to this tool, which I think is really cool, and hopefully will enable some the ability to do sort of meta optimization using this reach study as a tool to sort of give a score to how well a particular robot configuration works. We've also been doing a little bit of work in sort of the assembly side of things. This is a project by the National Institute of Standards and Technology in the United States. So essentially here we're trying to develop a framework for different assembly tasks. So not necessarily working on the tasks themselves, but trying to piece together sort of a framework to allow different users to really focus on those tasks and be able to integrate them with hardware quickly and integrate them into an application without having to spend a ton of time on this sort of boilerplate application code. We've also been doing a little bit of work with the open additive manufacturing framework as well, trying to plug in some of our motion planning tools to be able to come up with sort of trajectories that are good for additive manufacturing. And so we did a little bit of work in our labs here trying to do additive manufacturing using a weld torch. So some interesting work going on there. Again, we're also very involved in the ARM Institute in the United States. So we're working on a number of projects there, but it's sort of an interesting one here is this project where we're essentially trying to take a planned trajectory and sort of optimize sort of the motion primitives there so that we can try to keep the trajectory as accurate as possible, but then also respect the velocity constraints that we're trying to do with this particular trajectory. So generally there's a trade-off when executing a trajectory between speed and path accuracy. And so we're trying to figure out how can we break up a trajectory into motion primitives that tries to keep it as optimal as possible where both those things are concerned. I'll briefly see this one as well, but we've also been doing a little bit of work on sort of what I call meta planning. So for some of our planning solutions for raster patterns, right, if not all the points are reachable, then the entire plan just fails. And so been working on sort of an internal project at SwRI to come up with this meta planning framework to give you some rules to handle exceptions here when waypoints aren't reachable and trying to ensure that, you know, if you can take advantage of different kinematic setups or tool setups as well. So in addition, we're also spinning up an internal research project to try to tackle coordinated motion in a little bit in a better way where it's free of infrastructure changes. So a lot of our work in the past has sort of required infrastructure changes to support coordinated motion. So that's like using indoor GPS or AR tags or other things like that. And so we've gotten a lot of feedback from our customers and end users that that's not really a feasible way of doing coordinated motion. And so we're trying to spin up a project to investigate ways of doing this without having to modify infrastructure in facilities and really leverage sort of the full capability of a mobile system with a robot mounted on top. And so I think we'll be contributing back to a number of projects and hopefully we'll be able to share a lot of great results from this particular project in the coming months. Yeah, and so the last thing I want to touch on here, we talked a little bit about it earlier today, is trying to come up with an environment where we can use a lot of these ROS industrial tools sort of in a CAD environment, in a user interface it's a lot easier to use. And so we've spun up this project internally at Southwest Research that we're calling SWORD to sort of tackle a lot of these problems. And so the current tool that we built is a plug-in to the FreeCAD system. So, you know, we're trying to target a lot of these capabilities that we discussed earlier, things like importing geometry of your robot in a CAD format, being able to build up URDF visually, modify it, be able to generate collision shapes using convex holes and convex decomposition. So we're trying to integrate all these different tools into sort of one place where we can use that. So then also sort of extending that to this whole scan and plan framework as well, being able to import parts, generate tool paths on the parts themselves, and then sort of having the motion planning environment exists inside this system as well, so you can really tune how the motion planning works, and yeah, and really get a feel for what the parameters are and what sort of planning setups that you need for a particular application. So we're getting really close to a beta release for this. So if this is of interest to any of you guys, please let us know. We really would be happy to get feedback on this and let you guys kick the tires on this particular piece of software. So yeah, so just sort of to wrap up here, some common themes across all the work that we're doing here is that there's really a need for improved compatibility and a lower barrier to entry for a lot of our tools. So I think that's going to be something that we really try to focus on in the next year here, is making things available both in ROS-I and ROS-II, and again, trying to look at cross-platform, right? So we can use these tools on Windows and Linux and really try to broaden their availability to everybody who wants to use them. And in terms of lowering the barrier to entry, also trying to distribute a lot of these tools via the ROS build system, making Python bindings to make them easier to use, providing some more documentation, and we're calling it kind of snackable content, so like short videos that sort of display how things work and all those things, as well as continuing to improve the capabilities that we have as well. So I won't belabor this here, but we've also put together this big list of resources. Feel free to take a picture, or we'll distribute this as well. But there's a lot of resources that we provide through the ROS-I Consortium, but definitely check those out. And yeah, if you have any questions about the tools, feel free to open issues, pull requests, contact us directly. We're really happy to have these tools be used and make improvements to them. So yeah, but anyway, thank you for your time.